Hi there. In next video, we are going to see quantum phase estimation algorithm. Before that, let's quickly revisit the phase kickback effect. So in phase kickback notebook, we saw that there are some type of controlled operations where control gets affected because of the state of target qubit. So here we saw that when we apply this operation, q0 gets affected because of the phase of q1, and this q1 remains unaffected. We also saw this example that when we apply c0 to plus minus state, this minus state affects this plus state and it becomes plus to minus, and but this minus state remains unaffected. Also, we saw its application in phase oracle and Dweck-Joja algorithm. Now let's see what are the conditions which we can keep in mind to remember that phase kickback effect is going to happen. So first thing is that there must be some kind of controlled operation being performed. So yeah, for C0 indeed control operation is going to be done because C0 is controlled operation. Then another condition is that control qubit should be in state of superposition. Yeah, it's plus state here. And then target qubit psi, means this one, should be eigenvector of control unitary gate u. Means what this means that it should hold this equation true. So if unitary gate u is applied to state psi, then psi should be remain unaffected, but some state some value e power 2 pi I phi should be multiplied with this state psi, and this 2 pi psi will always be equals to 1. Now let's see that if we apply NOT gate to this minus state, it holds this equation true or not. So let's unitary gate is x gate and qubit psi is minus state. So when we apply x to negative or minus state, then here it's u, but yeah, it's x actually. We can expand minus as 1 upon root 2 0 minus 1. When this x state will go inside, it will convert 0 to 1 and 1 to 0, which by taking this minus outside, we can write it as minus of minus state. Now if we compare it, we can clearly see that when u is applied to this when x is applied to this minus state, then it gives us minus of minus state, which is equal to lambda psi. So clearly we can say that this psi is eigenvector, or this minus state is eigenvector of this unitary gate u, and this minus 1 is eigenvalue. So in this expression, this is unitary gate u, this target qubit is actually eigenvector, and when this unitary gate is applied to this eigenvector, it gives this eigenvalue, and then this eigenvector as it is comes out. So for this operation, we can clearly see that all these conditions are holding true. That's why we are able to see the ideal phase kickback effect here. But even if this equation is not holding true, then also there's some kind of entanglement will happen, but it will not be as apparent as when this condition is met. Now let's see mathematically how this plus state got converted to minus state. So here this at this point we can see that psi 1, and psi 1 was plus minus. After applying C0 gate, here we have psi 2, and for psi 2 here we have x gate, and plus state I can expand as 1 upon root 2 0 plus 1. I expanded, and then I multiplied minus 1 with both 0 and 1, so it's like this. Now if I apply this controlled x gate here, so this term will not affected because here control is 0, so this term will remain as it is. Now if I apply here, so this control is 1 here, That's why control C NOT gate will be applied here. And we saw that when NOT gate is applied to minus state, it gives lambda, and that lambda is -1. So here we have this lambda, and just above we calculated that lambda is -1. So putting value of lambda as -1 here, we got this thing. From this one we can take this minus state outside of equation, so it came here. And then we have 1 upon root 2 0 -1, which is nothing, it's minus state. And writing it like this, we can see that we started with plus minus state and we have this minus state. Now here you have one quiz. Here we are our control is in plus state, means it started with 0 and head mark got applied, and our target is in 1 state. So when we apply control G operation, what will be the output? So you can use same formula to calculate what will be the, first you need to calculate what happens when G gate is applied to 1 state. So what is the value of lambda, and then after that you can calculate what happens when this control operation is applied. And we will see same thing in quantum phase estimation also. So there we will see how this circuit will work. So yeah, thanks.